Hello, I am Frankie Celantano of the Virginia Military Institute, and I'm our team lead.
I am Joseph Lieber, and I am the mechanics lead.
And I'm Michael St. John, the electronics lead.
And for about the past year, our team has been tasked with designing and building this rover, whose primary purpose is to reduce the population of ticks in residential areas. As you can see, the rover's design is fairly rugged to allow it to operate in adverse weather conditions like a light rain or over muddy terrain. Before I get into the technical details of the system, however, I think it's important to provide you with a background understanding of ticks so you can understand just how important this system is to our communities.
Ticks are parasites that live in all 50 states, Canada, Mexico, and many other countries. CDC data shows tick-borne illnesses have risen dramatically. In many areas of the Northeast, over 50% of adult ticks are infected with Lyme bacteria, causing the disease to triple since the year 2000. Since ticks only feed 3 times in their 2-year lifespans, they have an extraordinarily low energy budget and spend most of their time in a state of suspended animation called stasis. Ticks wake up from stasis when they sense vibration and CO2 and begin questing for a host, as can be seen in the photo, by climbing to the top of grass stalks where they extend their barbed legs, hoping for a host to brush by. The current gold standard to remove ticks is to use bottles, such as these, to spray their environment with a powerful acaricide, such as permethrin, which, although highly effective, is also toxic to many animals. A better method is therefore needed. We designed this robot to reduce tick populations. The rover uses biomimicry to encourage the ticks to attack it. It wakes the ticks from stasis using vibration from the wheels and CO2 dispensed from dry ice canisters. Ticks attempt to latch onto the rover's skin, a permethrin-infused fabric, where they absorb a lethal dose of permethrin and die within seconds. Unlike chemical spraying, this leaves almost no residual permethrin in the environment. Other researchers have shown that ticks in residential areas are concentrated between manicured lawn and woods or fencing in regions known as the ecotone. The rover patrols a navigation wire placed around the ecotone while exuding a CO2 chemoattractant. The main components are shown in this CAD model of the system. They are the tick collection wings on the sides, the twin magnetic navigational sensors on the front, a tick collection drag cloth in the rear, and an electronic control box in the center containing the majority of the circuitry and microcontrollers. The electronics can be divided into 7 main subsystems. The power supply subsystem provides separate digital and analog power rails. Separate microcontrollers govern the throttle, steering, and user I/O systems. A radio frequency subsystem allows the rover to switch from autonomous navigation wire following mode to manual remote radio control mode if the robot temporarily loses tracking. Another subassembly is the magnetic field sensor conditioning circuit, which is used for navigation. The rover navigates around the ecotone using a system similar to a line tracking robot, but instead of following an optical path, we use a wire carrying an alternating current. This creates a magnetic field much like a wireless dog fence. The robot senses the magnetic field using 2 unshielded inductors in the front of the robot. The LC tank circuit's output is amplified by instrumentation amplifiers, rectified into a pulsing DC signal by a precision rectifier circuit, and low-pass filtered into a DC voltage proportional to navigation magnetic field strength. This signal is then sent to the steering microcontroller. 2 printed circuit boards are fitted with a water-resistant box attached to the top of the rover. The bottom board houses 2 separate power subsystems, which are needed to prevent noise from digital components from affecting the small analog magnetic field detection circuit. They also house a low battery alarm and a multiplexer which allows the rover to either autonomously follow the navigation wire or manually with a remote radio controller. Manual mode is useful if the robot loses tracking, so the user can drive it back over the wire. The robot uses 2 different types of motors, servo motors to control the steering, and DC brush motors for the throttle. Twin high-current DC servo motors in the front and back of the rover provide 4-wheel steering. Their H-bridge PWM circuitry is encased in the servo motor, so they only require a low-current PWM control signal from the control box and high-current power from the battery. Twin DC motors in the front and back provide 4-wheel drive through locked axials. These are driven by discrete H-bridges called electronic speed controllers that are waterproof and located underneath the control box for thermal cooling. The top printed circuit board houses the throttle and steering microcontrollers. It also displays the rover's battery life, speed, and the strength of the magnetic field on LCD displays. The top printed circuit board also houses the web server, which sends information about the robot to a mobile device up to 200 feet away. Tilt switches help the user debug problems in the field. If the robot is powered on while held vertically upwards, it disables the throttle, so only the steering servos turn when moved over the navigation wire. Turning the robot on while held sideways causes it to ignore the magnetic sensors and instead drive in a figure-8 pattern to test the throttle motors. The rover is fitted with fabric-covered spring-loaded wings on both sides and drags a fabric square in the rear. The fabric surfaces mimic animal skin and are sprayed with permethrin. Twin silver CO2 releasing chemoattractant containers are filled with dry ice, or frozen CO2. The CO2 wakes the ticks from stasis and encourages them to feed on the rover, where it absorbs a lethal dose of permethrin from the fabric. The signal for the ground navigation wire is created with a custom function generator, which we call the base station. It creates a constant AC current through a navigation wire that can be 1 foot to 1 mile long. In the demonstration video, the system is connected to a 10 ohm, 20 ohm, and 30 ohm resistor individually, off camera, to show its ability to react to changes in wire resistivity. To accomplish this, a microcontroller develops a 7 kHz square wave that is sent through a low-pass filter to extract the fundamental 7 kHz sine wave, which is then high-pass filtered to remove the DC offset. A proportional integral controller in the microcontroller sets the gain of the signal using feedback from a current sensing resistor so that the system achieves a 45 mA RMS current in less than 3 seconds after the system is turned on, regardless of the length of the load wire attached. The base station also reports the battery voltage and the loop current on an LCD. A low battery indicator sounds a loud alarm if the battery is discharged below 6.2 volts. A push button temporarily disables the alarm should the user need a few extra minutes of runtime. To simplify operation, the base station uses the same type of battery as the rover. The electrical components and circuitry are encased in a weatherproof container. It was our first experience designing printed circuit boards, and the first one did not work. Debugging was slow and required installing and testing just a few components at a time until each subsystem was confirmed to work. The images displayed represent the final PCB designs before printing. The next stage for the TIC rover is product development. The robot will first be field tested by an undergraduate biology team at the Old Dominion University in the summer of 2020. These tests will measure the degree and length of time that tick populations are reduced with different treatment plans in a residential environment.
The results will then be shown to venture capitalists to determine if they will finance the tooling, material costs, and engineering for a small production run of these rovers. Hopefully, the venture capitalists will then seek out a manager to sell these rovers to entrepreneurs interested in a tick treatment business. These small businesses could target personally owned residences, equestrian industries, and even the military to clear training grounds.
Additionally, the rover has the potential to be re-engineered to target other pests such as cockroaches in food processing plants, bed bugs in hotels, or carpenter ants in lumber yards. So while our technology is still in its infancy, the approach we use of robotic biomimicry to target pests has many potential applications.